Hello, everyone. Welcome to the Y-Axis Pod. I am your host, Tristan Ivor, and today I have with me Tarun Chitra. Tarun is the founder and CEO of Gauntlet Network. Gauntlet is a company that makes crypto networks and their governance statistically sound, which means that they actually mathematically model the different occurrences that could happen across these networks and help founders make the correct decisions in what they do. Tarun, thank you so much for coming on the show with me. It's great to have you.
Hey, great to be here. I think the last time we did a podcast was like January 2021. So, we've both aged 10 years since then. So
yeah, it's been a couple roller coasters since then. Since that, I will never forget the chickens pulling the carriage analogy. That was always a good laugh. And for those that don't know Tarun, Tarun is crypto Twitter's in-house mathematician. He is the one who graces us with different mathematical talk from time to time and makes us realize that there is a whole world that we do not understand, that we do not know, and that it would be nice to have a little glimpse into. On that note, Tarun, I would love to know why math. Like, why did mathematics stand out to you? Why was it a path that you decided to pursue when I'm sure there were a lot of different things you could have done?
yeah, I think the honest answer is just, both my parents have PhDs, and when I grew up, we did a lot of like math contests and science contests and stuff like that. So it was sort of like built into my early days. But the irony is my parents, when I went to college, were like, don't do math. You should go be a doctor or do something like that. And I decided not to do that. And I guess that things worked out okay, but it was very funny that two people, one who has a math PhD, were like, don't do the same thing as me. But I think the more like philosophical reason I find it beautiful is, math, when you're taught in grade school or even in college classes, is, about function, not form. It's really about how can I use this thing? Like, why did I learn calculus? Well, it's because I need to use it for physics, for understanding mechanics. Or why did I learn algebra? It's because, I needed to write a chemical equation and balance it, right? There's sort of this sense in which it's taught in a way, at least in the US, where it's all about functionality and like little about form. There's little about the aesthetics and beauty of it in that form. But pure math is more in some ways like art, right? You can show the same result in many different ways, but some of them are more elegant because they're shorter. Some of them are more elegant because it doesn't need as fancy of theorems. Some of them are just elegant because they're sheerly just insanely impossible to prove. Like the actual proof itself is so unique in some ways. And some of them are just, because it's something where it's like the statement is so simple, and yet it took people millennia or hundreds of years to solve. So I think those types of things are the reasons I like it, and then of course, because of, what we do at Gauntlet, we spend a lot of time trying to understand, and you continuously run simulations against different protocols and observe when they have particular risks and then send governance proposals. So it was a busy night last night. But the thing is, like, having really good quantitative tools is important to scaling big systems. And so, what I do on the applied side is more math that has function. But, of course, I like find the math that has form, that you have for its sort of aesthetics a lot prettier. And I think a lot of people in crypto, AI, etc., are, they're not, they know math from the perspective of, like, how can I use it? Where do I use it? Right. And it's quite deep in both fields. But crypto, unlike AI, actually has more of the sort of pretty aesthetic math hidden under the covers, in the math for zero knowledge proofs and the math for particular types of elliptic curves and signing and stuff like that, which is much deeper than gradient descent, Go-Burr in AI. And so I feel like people in crypto are more open to the glimpses of the beauty in pure math that maybe other people aren't. But I don't think I've gotten to use much like pretty math in any papers I've written. That's just the way the cookie crumbles, I guess.
I mean, I have a few questions stemming from that. So, first question was, what was a moment for you when thinking of math from the perspective of form rather than function that you were blown away, that you saw something and it just made your mind melt and consider the world in a different fashion?
Yeah. I think when I was in middle school or high school, I forget. I think high school. Just like having an understanding of the difference between infinite objects and finite objects. I think like really understanding that infinite objects and finite objects can have very different properties, and B, that there's multiple types of infinite objects that aren't equal to each other. Those two facts are Cantor, who proved the second fact, that there are multiple kinds of infinity and they're not equal to each other in some way. You can't line the objects up one by one and make a correspondence between them one to one. Was when he proved that fact, his advisor, his PhD advisor, sort of abandoned him in the 19th century, and then he killed himself. So, sometimes I think that type of stuff is very crazy. But one of the more I was really blown away by things is there's sort of a thing you probably learn in like high school algebra or middle school or whatever, which is the fundamental theorem of algebra, which is that every polynomial of degree n has n roots in the complex plane. So you can always find the roots of things. So when you learn the quadratic formula, you're writing a formula for finding the roots of a quadratic equation. But it turns out you can't write formulas for arbitrary degree polynomials, and that was sort of a big thing in the 19th century. But you can show there exists these roots, and there's only a certain number of them. This is probably just like a fact that people use all the time to casually state it, but it often, you don't really see the proof for it until later. And I remember the first proof I saw was just really ugly, and I was like, I can't believe that people spent so much time doing this. But then I think in college I was taking this graduate complex analysis class, and there was like the most amazing proof of the fundamental theorem of algebra. It was just like one of the most elegant things I've ever seen, because it was able to prove this very deep fact in one line. And it was a deep fact that I had like sort of internalized just as a rule forever, right? It's just something that's like, okay, yeah, sure. Every symmetric matrix has a bunch of eigenvalues. Every polynomial has as many roots as its degree. But it was one of those things that like seeing the same thing done elegantly was more mind-blowing almost than the fact of the thing that you're seeing.
I mean, that leads kind of perfectly into my next question, and excuse the wind here, but how does one go from a messy, perhaps dirty representation of an equation to a cleaner, simpler, more elegant, more beautiful form? Is that an independent mathematician who is working on a different problem that stumbles across it? Is it somebody that grabs an uglier representation and spends a lifetime honing it down? What does that look like?
Yeah, that's a good question. I don't think there's like a one size fits all answer. Sometimes it is exactly what you're talking about. Someone just grinds through and finds a simpler way. Sometimes it's many years later, a new type of math or a new subfield is made, and in that subfield, the abstractions used make it very simple to write the proof. And in the process, people created those abstractions. Sometimes it's because people created those abstractions to simplify the proof, but sometimes it's just because it was for a totally different thing, and then along the way, you found this kind of simpler route. And then the third type, which I guess is the type I personally find more exciting, is when someone in another field uses intuition that they've developed completely differently, finds a solution to the problem because they're just sort of like thinking of it in a totally different axis, or they're writing down the equations in a way that's very different. So a couple examples of this are, there's a very famous physicist named Ed Witten, who is at the Institute for Advanced Studies. He's probably one of the most well-known theoretical physicists. Arguably most of string theory exists because of him and a couple other people. And Witten is the only non-mathematician to win the Fields Medal because he found a way of reproving something called the Morse Conjecture in a much more simple form, because he was thinking of it by trying to map the problem to a physical system and then show that the physical system has some properties, like the particles can't reach a certain state or they can't touch a certain point. And in the turning into this physical problem, you use physical intuition to like back out sort of an abstract math result. So that's an example of one where it's someone from another field. Another example that's much closer to cryptography is there is a property. There's sort of a thing called a randomness extractor. And a randomness extractor is something that I guess I can describe maybe via sort of an allegory. But suppose that I have a coin that has 10% chance of, when I flip it, I get a heads. You would probably call that coin less random than a coin that was 50% heads, 50% tails, because you're going to get tails a lot more. But one question you might ask is, can I replicate the 50% coin via the 10% coin? And so the way you do it is you say, okay, I flip the 10% coin, and if I get 2 heads in a row, I reject, or I get 2 tails in a row, I reject, and then I keep flipping. But if I get a heads and a tails, or a tails and a heads, then I call one of that heads and one of that and the other one tails. And the reason for that is there's an equal probability of getting head tails or tails heads. And so you conditional on only those, you get 50-50. So this is what's called randomness extraction. Like, I'm able to take some source of randomness, it's not as random, and like make it more and more random by doing some manipulations, by sampling it in a particular way, rejecting things, whatever. So randomness extraction is extremely important in cryptography because oftentimes you're just given a sort of crappy source of randomness and you want to increase how random it is. Maybe that's what a hash function is doing for you. Maybe that's what, other places you get randomness in a computer that are used where that happens. And so randomness extraction is actually extremely important from the perspective of, like, if I need a really good random number for a crypto system to work, so I can choose a random point, then I need to understand it really well. So there was this computer scientist, Zeev Dvir, working on randomness extraction in, I want to say, the 2000s, early 2000s, mid 2000s. And basically, there's this outstanding math problem, like pure math problem, called the Kakeya conjecture, finite field Kakeya conjecture. And he accidentally proved it, and he proved it really simply using very simple elementary math. Like, you could have basically understood his result with high school math only. And it'd been an open problem for almost 100 years, 80 years, something like that. And people had tried throwing bazookas at it and using really hard, complicated math, and like completely just missed the fact that it's actually very simple proof. And so interesting thing is I think that was the first time I had ever encountered. I was an undergrad when this happened. It's like 2008 or 9. And I remember reading that paper, and I learned about this thing called the Schwartz-Zippel lemma. And the reason I'm mentioning it is it's probably the most, if you ever read any books or papers on zero knowledge proofs, it's like the #1 used property, which is basically, it says that, if I give you two polynomials and you show that they're of a particular degree, and you show that they're equal at a certain number of points, then the probability that they're not the same is really small. And it turns out this randomness extraction result is very related to that. So there's kind of this very funny thing of like this person in CS trying to do some cryptography thing, 30 IQ'd it and tried to like not go to like use the hard math to solve the problem because it sounds like a hard math problem, and then kind of was able to solve it and use this stuff that's actually very weirdly related to ZKPs. So I actually didn't know much about ZKPs then, but that was how I actually the first time I ever really ran into them was 2008. Was reading this thing, because I was way more in pure math land then, and I was not like paying attention to CS stuff. There's a couple other examples I have of this type of stuff, but yeah. Anyway, long story short, there's a lot of different ways it happens. Some of them are more surprising than others.
Okay, wait. Before I ask you about zero knowledge stuff, which we can get into in a little bit, one quick clarification for myself. When you're talking about this random number extraction, are these points on like the elliptic curve or nothing to do with elliptic curves?
Yeah. So it could be random. You're choosing a random point on an elliptic curve. So one reason for doing that is I might, if I want to generate a public-private key pair, I might choose a random point and then figure out what and make that the private key, and then choose a public key associated to it by computing its inverse. But the point is, like, if you don't have very good randomness, like let's suppose I flip a coin and the entropy from that coin picks the random point. Well, suppose there's a billion points, but there's only 20 different outcomes for the coin flips. Well, then I can just flip the coin 20 times, figure out what the 20 public keys are, and reverse engineer or private keys and reverse engineer the public keys and figure out which people are using the same ones, right? This was actually exactly what happened in the, I forget what it was called, the fatality exploit. It's called fatality, it was something like that. It was like this thing that generated vanity addresses for you.
Oh, I remember
that had a certain number of zeros, and it had not enough entropy, so like people were able to find it is exactly that. So very good randomness is extremely important in key generating keys in cryptography. So
got it. Okay, so my deeper, perhaps dumber question to sort of what you just elucidated on is, do people create this and bring it into existence, or do these things exist in nature? And by that I mean these proofs, these theorems, these things, are they transmuting it from nature into a written form, or are they creating a, is an angel being born, I don't know what the best way to describe it, virginal birth or something?
So it's a very good question. This is also, again, gets back to this form versus function thing, because for things where there's function, you don't really need to justify why you're writing down particular equations, because you're like, hey, that thing explains why, like, the path of throwing this ball is a parabola, or it explains why ... Like I see the scientific result where I get some data and I'm able to deductively show that this math happens to replicate that data all the time. So I'm pretty confident that it's right. Pure math is the opposite, in that what you do is you say, hey, here's a set of properties. Here's a set of rules that I want to have. So the rules might be, say I want to define the natural numbers, which is like the numbers 1, 2, 3, 4, ... I might say there's a set of rules that define those numbers. Like there's an increment operator that goes from 10 to 11 and 11 to 12 and 12 to 13. I might say there's some rules that say, like, hey, there's a way to count the number of elements less than you. So I can say there exists a function that says, hey, if you're the number 20, then there's 20 things below you. And then there's a sense in which, well, why even have the labels 1, 2, 3, 4, 5, 6, 7? I could have a totally different set of names for them, but as long as they have the same properties, like there is a element that has 7 elements less than it. There is an element that has a successor who has 8 elements below it. I can actually strip away the actual names that we give them and talk only about the properties. And so once you have those set of properties, then you say, hey, I want to prove some theorems that given these properties, this set of things must be true. And much of the 1930s through 50s in logic, which is sort of the formalization of set theory, the formalization of these types of rules, was actually finding impossibility results. The impossibility results sort of say like, hey, if I choose two slightly different rule sets, I can find theorems that are true in one and not true in the other. And this is sort of like says that you can, even the choice of picking these rules is quite hard. And in a lot of cases, a lot of mathematicians don't really, they're just like, whatever, we'll use the rules that people have agreed on socially. But there are some things that are just very, and most of these rules, so I should take a step back. Most of these contradictions actually come from like these particularly weird infinite objects. If you're, say, someone who does not believe in infinite sized objects, then there's no inconsistency. There's like a very clear set of rules that you can deal with. But you also can't get things like, for instance, like you can't really explain a neural net as a computational model in the finite world. So there's also some very weird things. If you say I don't believe in infinity, then you have to explain like why certain other things work in practice that the theory shows depend on there being infinite sized objects. Anyway, that's maybe a more complicated way of describing it. But the idea is like once you pick a set of rules, then you try to show some properties that any objects that satisfy those rules have to satisfy. And Gödel in the 50s showed that the natural numbers, just this counting number, is very simple. They only really have those two properties I told you, which are there's a certain number of elements below me, and there's an element above me that has one more elements below it than I do, right? Successor and number things below me. And Gödel showed that there exist true statements, so statements that are true about these things, that you can basically never prove true or false using just those properties. And it's called Gödel's Incompleteness theorem. Very famous result. And it's sort of a bit of a very surprising, kind of one of those really crazy things.
Okay, but you're sorry, real quick. I feel like you're being very diplomatic here. Let me rephrase my question and see, and I kind of want your opinion. And maybe this is a more eloquent way of phrasing it, but are theoretical mathematicians, or those coming up with the most elegant proofs that exist, transmuting knowledge or pieces of things, matter in existence, into this theorem, into this proof? Or are they doing acts of God, like creation? Are they creating?
No, it is sort. This is a good point. It's sort of not really creating something new, but choosing what properties you care about and then figuring out some result from that. It feels like creating something new, right? It really does. But it's sort of like, well, this theorem, if it's true, then it was true before you found it, right? It's just that you found a way to describe it and then demonstrate that these are the sufficient properties to make it come true. But there's a sort of it is effectively this type of thing where it's not deductive, where you found something in nature and you repeat something a bunch and you're like, all right, I'm pretty sure this is it. It is definitely more inductive, like, and inductive properties sort of have this sense in which they were true before you found them. You just happened to find them. So in that sense, it's not like an act of God, although, Gödel also has this very funny proof called Gödel's ontological proof of God, which, it was sort of a joke, but it kind of.
This is the one where it doesn't matter if God exists or not because the results would be the same on either side.
That's like one way of viewing it. Like, yeah, it's sort of a little bit of this this way of like, you kind of get to the idea that like, given the properties, sort of, if a god existed with a certain, with the ability of having all properties that are stronger than all properties humans had, then effectively this god has to exist. And it comes from trying to like write down the properties of this creature and then proving statements about it. And the only thing that could prove statements about itself is the thing itself. That's sort of,
Yeah, that okay, that's a better representation than the one I had in my head of it. Um, so question for you, I guess. You've been deep in this world of induction, and when you're inducing, I'm sure it brings up a lot of questions because you probably have to question yourself all the time as you're going through these inductive processes, you don't have a deterministic route a lot of times to get to what you're trying to get to. Where has that left you as far as thinking of, like, okay, maybe an easier way to state this is like, are you Newton or are you Leibniz? Like, are we like predetermined sort of, things just moving the course, or are we kind of, you know I don't know, I don't know how to describe the other side of it, but you know these free-willed creatures creating our own path through our creation and through the things that we do in our lives.
yeah. Um, I am more of the mindset of free will does exist, but it's sort of bounded. So I'm hedging. I'm sort of like, I'm willing to believe that it does exist, but like it doesn't exist in some absolutism. Like you don't have it your whole life. You don't have it all the time, but you are able to have it at particular times.
Okay, I mean, that's fair. So there's like just these. Okay, I think that's fair. Do you think, okay, maybe I'm probably pulling at straws here, but is that like a little bit along the lines of, there's a lot of periods of our life when we're in autopilot and our brain is just, kind of running itself and we're going through the motions, and then there are those rare moments where we are fully present and in accord with whatever decision we're making, and we are fully there with it. Is that sort of perhaps one of those moments, or?
Yeah, but you can't always be in that state. That's kind
Oh
of
yeah,
the
it'd
thing.
be like incredibly overwhelmed. There's no way, right? Like we're reductive creatures, not
Yeah,
encompassing creatures.
yeah, and there's lots of constraints when you have multiple creatures who have to interact, right? So it's like those constraints are certainly,
Right.
you know, quite detailed and very hard to even enumerate. Uh, it's a bit of a non-answer, I guess. But I just feel like people hope the free will debate just feels to me like there's people on the both edges being like, this side is true, and I'm just like unwilling to believe. I just would prefer to be like, well, sometimes both. You can see instances where both kind of make sense. It's not like
Mhm.
you're always in one.
And is it taboo in sort of the math community to I guess be spiritual, to go beyond the theorems, to go into this, you know, some would call it wishy-washy, some would call it accordance with something else. I'm just curious, is that like, is in practical math, I know that's the case, but I'm curious, like in theoretical math, like, Einstein said some very interesting things which you wouldn't think a mathematician would say, and I'm curious if it's a more open conversation there than it would be in other places.
Um, I would say one thing, which is I actually think scientists tend to be much less open to spirituality than pure math people. Uh, but they're actually ironically into very weird spirituality, not the super open spirituality. I just think empirically, I know more religious math people than I know religious like physicists or chemists, and I think it just comes from the fact that if you're really rigid about following rules, there's two ways to get into math. One is you like it for the aesthetics or the problem solving. The other is you really like really rigid rules, and so it attracts a particular type of person. I don't know how else to explain it, but I've always observed this difference where there's just so many like religious people in math and like very like strict religious, like Catholic or like strictly Jewish, like Orthodox, or really Hindu, like, you know, the famous mathematician Ramanujan, who like was in India and then went to Oxford, and he never really, he just like was never formally trained, but like created all these, solved all these random problems. Kind of like the stereotype of like the Goodwill Hunting genius type of person. Like he's like the inspiration for that. And that guy killed himself because he thought that like a demon spirit from his village was like haunting him, so he stopped eating.
Whoa.
So all I gotta tell you is it's there. On the other hand, actually, in honor of a person who died today, you have the other type of math people, which was the really crazy esoteric ones. I don't know if they're spiritual, but they have very solid crazy beliefs. And the person I'm talking about is Theodore Kaczynski, of course, the Unabomber,
Yep.
who was a math professor and then left
I didn't know
academia
that.
and lived in the woods. Yeah. He's the documentary on him is actually very good. Highly recommend watching it. But yeah, you know, I think there are spiritual, but not in the way you're thinking. That it's
Mhm.
not in the like I'm going to Burning Man, or I'm going to, you know, like South America. It's definitely more the like militant following rules version.
Got it. Okay, yeah, that makes a ton of sense. Thanks for exploring a random pathway there with me.
That's just my observations. You know, I have no uh yeah, I have no like I haven't done an empirical survey or something. It's just that like over the last whatever 35 years, I these are the thoughts I've had
Yeah, I
about
mean,
this.
you've been around a lot of mathematicians. You've probably studied them more than most people. I mean, I was just curious because I've seen a little bit of what you explain represented just through reading different things over time. So I was curious on your perspective. One thing I also want to touch on before maybe going to ZKs, because I think it'd be really interesting to talk a little bit more about ZKs, is nowadays, I know physics is a really hard field because a lot of people feel that most of the at least obvious problems are solved and there's very little large step function innovations occurring. And so I've heard this expressed by different sort of physics PhD students and people that I've met that they feel bounded by what they're pursuing. What is the case with theoretical mathematics? Are there like what is the pathway for somebody that is absolutely in love with math, wants to study it, wants to go as deep as possible, but also wants to have an existence in our system where they can support themselves and their family? What are pathways available to people wanting to do things like that?
Well, first off, I never got PhD and didn't do, and you know, I sort of got waylaid. So I can say you can still be very into it and not have to have uh you know committed in some way.
Oh, totally.
Uh, and one of the real reasons is you don't need money to do math. Like you really need like a notebook and a pencil and the internet. I think it's very different than fields where there's a lot of money needed to like do experiments or like to like uh, fund building particular technology is very different than um, you know, doing something like uh, uh, something, yeah. something where the startup costs are really high. Now, theoretical physics arguably is something where there's a similar no startup cost, but for some reason, and I don't know why exactly this is, but like theoretical physics has more cranks and like nonsense papers than math, and I don't totally understand why. But because of that, people are very socially uh, uh, socially um, uh,
Your
against
diplomatic
people
engine.
who yeah, socially kind of just like not um into people who aren't trained at some institution, whatever. So it's kind of interesting, even though, you know, I think theoretical physics in the 90s was more open to this. I think somehow the internet actually created so much spam that it went back to like institutional. Whereas for math, I think actually for some reason it's actually there are tons of cases of people on their own making discoveries and stuff like that. The physics case, a really good example is do you know those guys in that meme with the dump it? You know, they're on the phone.
Bogdanovs?
Yes. Do you know they're famous for writing a crank theoretical physics PhD?
No, I did not. I did not.
Yeah. There's
When you say
there's a
crank,
thing
what does that mean?
like, you know, it's like looks like it was made up. It's not formally correct, like the proofs are wrong or like the statements are wrong, but they use all the right words. But this is the thing where they basically made up this thing that's just like completely false. But they were already famous on because they had the TV show or whatever.
Okay, that makes sense. I'm gonna put that link in the description so people can go take a look through it. What about mathematicians though? I do understand this, that you're saying that it's a much more open field in the sense that you can have some guy with a notebook in India, and if he's excellent and is able to represent that through the internet, like he can grow in the field. But do you stay in a world of research, regardless of PhD, I'm just saying like very talented mathematicians, what are sort of things that they can focus their time and energy on that you think are worthwhile or interesting?
Um, I mean, for at least for me, I always, like I said, the thing I've always found most interesting is stuff where you can translationally do math. Like you're trying to solve some problem in some other field, and then you accidentally find some math or like a different representation of some math. And I think arguably the way I kind of was able to find some success in crypto was basically doing that, where like in 2018, 2019, when the first sort of vespers of DeFi were coming out, I was doing numerical simulations and writing formal papers on like different properties of these systems, like trying to prove some formal results of when they work and don't work. And the fact that you had DeFi protocols that people were putting money in and they didn't blow up or they survived for a while was sort of like evidence that there must be actually some sort of math behind it. I think for AI, there's something sort of similar, but it's less. Yeah, it's just like not. It's just like not as clean as crypto. Crypto actually has a lot of ways where, you know, you do it's actually important to have a good mathematical foundation, and B, it's effectively necessary, not just sufficient. I think in AI, it's actually quite a bit the opposite.
Is that because you're dealing with infinite objects, like you were saying, or nothing to do with that?
Um, yeah, maybe it's not quite just that. It's actually like this idea that in cryptography, you're assuming this like adversarial model where you have to say like, here is how much computational resource the adversary has, and here's how much computational resource I have, and can I do something where I can create something where such that the adversary has to use hopefully exponentially more resources than I used initially to try to crack something. And that threat model relies on actually being quite precise about who the adversaries are, what functionality they have, how much compute they're using, etc. So you naturally have to formulate things a little more like rigorously. In a lot of machine learning, it's like, well, I have a model. I have some data. I don't really actually know. I don't know whether this model is even in the class of things that match this data. Like the model totally could mispredict, but you know what? I'm just going to try it and see how it works. And there, because you don't care about it being adversarial, like you don't care about the person trying to like give you bad data as much, and because you're averaging over many instances, you don't have to be as precise. Another way of putting this is like in machine learning and AI, you really care about the average case behavior. You don't care about the worst case behavior. Like the worst case behavior could be completely wrong. But in cryptography and finance in general, you care about worst case behaviors, and worst case behaviors need to have a model that you really, really have confidence in. Because like if I have the wrong worst case behavior model, then I'll just make completely wrong predictions about risk in a system. And so that's sort of like this kind of one of the reasons I personally found crypto a better place to be kind of a independent researcher, and find some of these types of problems.
Sounds like there's also just a thrill to it, right? I mean, you're kind of at battle. It's like a very complex chess game of sorts, and you never know when the enemy is going to try their thing, so you have to be prepared beforehand. It's almost like you're setting up this castle or this moat and just hoping that it'll be sufficient when the enemy comes. Is that a good representation?
Yeah, exactly. And you effectively, this means that you have to think about how big your moat is and how sharp your the rocks on your castle are, versus like in AI, you're kind of just like, I'm making a city, and like as long as it has everything everyone needs, I don't really care. Like yeah, sure, someone could come blow it up, but like less likely. Now, there is a whole field of adversarial machine learning, which is like, trying to get something to misclassify something, like the whole hot dog, not hot dog thing, right? Like you could trick it, or you can trick the language models, right? Like, and there's a whole thing of like, how do you do that? But it's sort of added in as an after effect, like, hey, like try not to mispredict these things, versus like, you will die if you mispredict this, right? Whereas cryptography takes the other lens, and the you will die means you have to be very precise about the events that could cause an attack to be successful, and then minimize the probability of those events. Well, what does it mean to have a good model, a threat model? You have to have a way of measuring that probability correctly. And in AI, you don't really care that much about the probability over the entire set of events.
Yeah, that makes immutable programs sound terrifying from your line of work, because you can no longer be reactive, right? You can only preset all the conditions and then that's it.
Yes, exactly. Well, but then again, also upgradability has the issues of like, opens your attack surface and whatever. So yeah, it's definitely a lot harder to write software in this world. And I think like people don't appreciate that. I mean, that's why people like us exist, and people like, auditors and stuff like that, because there's just so many different vectors, and you need these like kind of very concrete models. And anytime you need a concrete model, you're likely to have more formal math and less like, hey, I just like threw a bunch of things, I hope they work type of behavior. And there is a lot of stuff in AI. Actually, like recently I spent some time trying to read, like I was trying to understand some of the theoretical justification for why transformers, which are like ChatGPT, work. because they kind of just seem like, oh, it's like a random hack. Like, why does this architecture work?
Sorry,
And
can you
there
give
are
a definition of transformers?
yeah. So, a normal, maybe I'll go through the hierarchy. A normal neural network is just something that, have a function that takes there exists some function that takes a vector of n inputs. So, just some vector and outputs another vector. And there's a particular model that it fits to try to approximate that function. That model just is a bunch of matrix multiplication plus component-wise nonlinearities. So the original neural nets are feed forward. So that means like I take the input, I pass it through a layer, it does some linear algebra, does some nonlinearities, passes to the next layer, passes to the next layer, passes to the next layer. But the problem with that is it has no sequential, it can't do like sequential dependence. So like if I have text, like the words are like sequentially dependent, like the quick fox jumped, and now what I think the next token is depends on sort of fox, right? If I told you the quick mermaid jumped, right, that token now will be completely different by the context of mermaid. But these feed forward networks don't have that. So people then try to make what are called recurrent neural networks. Recurrent neural networks mean like you take an input, and as it goes through, it goes backwards. It gets allowed to jump backwards. So, as I go through that thing, like the quick fox jumped, okay, I need to predict the next word. The word fox might come back into my context. And now from that, I can say, but the problem with recurrent neural nets is they're really unstable to train. The space of possible recurrent neural nets, and this is where this infinite limit thing matters, is so big that it's like it's finding a needle in a haystack, and it's already expensive to train these things, so you're never going to get them to be stable. Transformers are feed-forward neural nets that have a hack, and that hack effectively replicates a lot of the features of these recurrent neural nets. And what it does is, you go through each layer and then you re-inject the entire input at each side. So what I do is I basically say like the quick fox jumped, and then I have to pick the next token. But what it does is it says, okay, actually the environment in which you're picking the token has fox and quick and jump in it. And using those words, use that to conditionally bias your next token. But it's not recurrent, and this is not like going backwards. It's just re-injecting the initial input at every time, so that you don't forget. It's sort of some notion of, and there's a notion of attention in these models. Attention just corresponds to like, hey, like fox keeps showing, like the quick fox jumped over the fence, the fox was red, the fox eats grass. If I give you those sentences, the word fox will stay in the context more in the sense that like when it re-injects the input, it says, actually, I'm re-injecting the input, but fox is 10 times more valuable than red. And as you're processing and predicting the next.
Makes sense. So then if you ask, where does it live? It knows that you're asking about the fox because that has the highest value. Got it.
So if you use ChatGPT, this is like why when you do the sequences of questions, the attention window is actually attending is the wrong word. Attending. I don't know what the correct verb is, but like to both your query, but also its output. So like if I ask, hey, ChatGPT or a transformer, what color is a fox? And it will output, North American foxes are usually red, but foxes in Africa are brown. I don't know. I'm making this up, but fox in Africa are usually brown. Now the word fox will be attenuated. Like it'll say that's an important word for the next query. That's what it means for attention. But it'll also make red and brown more important, which you didn't ask in your initial query. But because color and red and brown are closely related, or trained in the training set would be closely related, they get attenuated. So that's why as you ask sequences, it can actually learn from its responses, because it's effectively like that make sense? So
Yep. Yeah. No, that makes perfect sense. That's probably the best layman explanation I've had of this so far. So thank you.
yeah, I don't know why people like give such complicated explanations. It's actually, I find it's like everyone wants to jump to talking about like the neural nets and like the precise method for training and how you do the multiplications, and inevitably I feel like this is all just advertising for Nvidia by making it sound hard.
Oh man. Anything else on the AI front that you were still sort of mulling on?
I mean, I was just, I have a lot of friends who work in that space. Like, the, you know, a bunch of people who have been in it for like 10 plus years, like the CEO of Adept, or, my friend who's like the first employee of Facebook AI research, or my first boss is actually the head of DeepMind science division. So like, I've seen how it's changed over 10 years. And it's, every once in a while I get a nice surprise of like, hey, there's actually some theoretical real math result here, not just like bullshit like, oh, I made the model bigger and it worked better. Great. Why? Can you tell me why? Do you have any intuition why? No, you just want to go market to more VCs. Okay, I see. But and maybe that's my cynicism about AI stuff is like,
do you use it
is
for your work?
definitely for uh coding, but not really for queries. Although I think it's actually interesting that I sort of use it to replace Wikipedia sometimes. It's not like I definitely go and double check often, because it definitely fucks things up, but it oftentimes summarizes a Wikipedia article in a way that's easy to use. And, I think it's great. But, obviously it took 10 years to get here, and like huge amounts of investments. And like, I feel like people are not giving crypto that same kind of like time, but we'll see.
Yeah. I mean, I certainly am, but I
Yeah.
understand what you're saying. On the topic of crypto, so I know ZK, zero knowledge proofs, or zero knowledge technologies have been worked on before crypto existed. Why would you say crypto was sort of this perfect medium or expression for them, in the sense that I've now met a lot of very, I guess, famous or skilled cryptographers who couldn't really care much about crypto, except for the fact that they now get to work on ZKs in crypto. What's the like? Why did that connection happen? Yeah. What do you think about that?
Yeah. I think the main thing to understand is like ZK. So we have to sort of like separate a few different terms and a few different things that are going on in the ZK proof land. I think ZK as a buzzword was just to like sell VCs on a collection of technologies, investors in general, on a collection of technologies which include but aren't limited to multi-party communication, fully homomorphic encryption, zero knowledge proofs, succinct proofs, which are not zero knowledge, which is actually the majority of what ZK applications are using right now. They're not actually using the ZK part, but they're doing this using the succinctness part. And I'm trying to think if there's anything else I'm missing, but yeah, at least those technologies. And basically in the 90s, sort of when zero knowledge proof, late 80s, early 90s, when zero knowledge proofs were first created, they were created in this way where they were done via what are called Arthur Merlin proofs. Arthur Merlin proofs are this idea that like, I have some knowledge, I'm teaching you something, and we're doing it interactively. And I can impart that I have this knowledge without you ever knowing the thing. So like, I can prove to you that I have a red Lamborghini without ever showing you any proof that and without showing you the car. That's like one way of kind of saying it. The problem with these is that they were interactive proofs. So interactive means that like I need to do a lot of communication They're kind of impractical in some ways. There is this thing called a Fiat-Shamir heuristic or transform, which allows you to render these proofs non-interactive, but that came a lot later than the original ZKP. And ZKPs really came out of a complexity theory point of view as opposed to a practical point of view, in the sense that there's these different hierarchies of problems in computer science that have different complexities and how hard it is to solve. And you can show that two problems can be reduced to each other quickly if they're in the same class, but if they're not, then like one of them is sort of always has worst case problems that are much worse than the other one. And the interesting thing about these proving systems in general is that someone who has computing power capable to solving one of these harder computational classes can prove to you that they have an answer to an instance of a problem without you having to have as much compute as them. And so that's the theoretical reason that they came into being. Like I somehow have some weird way of solving some NP problem, and I can prove to you that the NP problem is correct. I have some way of solving the suspension of NP problem. I can prove to you that, and I can prove to you, the NP person, that it's correct. And this is actually this thing called a polynomial hierarchy, which is this idea that the amount of computation it takes to verify an answer can be much, much less than the amount of computation it takes to compute an answer. And that separation, that the proving between those is important. So that's what's called interactive proof. And sort of one of the seminal results in theoretical computer science is that interactive proofs, the set of things that can be proven interactively is the set of computations who require at most polynomial space at the input. So the ZK part was like, hey, I can do those interactive proofs and I can make them private. So I can prove to you that I have the answer and I don't have to give you the answer, but you can be certain that it actually satisfies these constraints. So this is all, so far, everything we're talking about is completely divorced from anything that vaguely sounds like an application. I remember in college, I sort of audited a cryptography class where we're learning ZK from someone who, Raphael Paz, who's one of the main sort of a very prominent ZK researcher at that time. And it always felt like there was like it was like there are these toy models. There's no real, you can't like do this for generic things. It's more so that you can prove these theoretical results, not so it could use practically. But in 2012, Gentry et al. Sort of proved that you can take any program, convert it to this particular sort of like matrix style of operation. And what I mean by that is something that looks like linear algebra. Like you can compile your code to something that is, hey, if I can show that these two matrices multiply and are equal to this other matrix, which all the matrices are derived from some properties of your code, then that is equal to proving that code worked, and you can do it sort of succinctly. And that was sort of the introduction of what's known as the rank 1 constraint system. I believe that was the first paper as a truism, but that paper is sort of very important because it showed, hey, there's actually a way of taking practical code and converting it to a simple-ish math problem. And then from that simple-ish math problem representation, you can do all the sampling, random sampling of it, and like get a ZKP. And that was sort of a very big deal. But the thing is, it was, again, somewhat theoretical. Like it was not kind of, you don't see people talking about it the way you see now. And again, remember, the theoretical reason for interactive proofs is the idea that I have some higher computational, I can solve harder problems than you, but I can prove to you that I solved it and you can verify it. And that's what matters. Blockchains are exactly this. In some sense, the proof of work problem is trying to approximate something like this. Proof of stake, a little bit different, but there's sort of a sense in which you need people to be able to verify that the network at large did some calculation correctly. But you don't want them to have to verify the whole thing, right? Like you want the light client to only have to verify some small, like your mobile wallet, to only verify a small thing, not have to know this whole state of the chain. And so blockchains naturally have this reason where you want ZK so that users, you can handle different classes of users, and you can also get sort of some of these verifiability capabilities that are inherently necessary to blockchains. And I would argue that the 2017 cycle funded, or really before, first so Groth 16, which is like one of the more common used ZK systems. It's what's in Zcash. Zcash sort of 2016-ish, 2015, I think 2016 kind of was the first thing to sort of like get these used in production, for privacy reasons. But I would argue the 2017 ICO boom, and to some extent the last cycle, funded a lot of stuff that's more for how do we get real compute in ZK. Like, can I, there's multiple different angles to this. There's A1, the roll-up version, which is I can prove to you that the state transitions on this other chain are correct, without you having to do that calculation yourself. There's the bridging version, which is I can prove to you that this balance on this other chain is correct without you having to be able to parse that VM. Then there's the coprocessor, which is like a smart contract, say wants a computation from a language model that's off chain. Well, can the language model give it a ZKP that it was run correctly on a particular set of weights? And now the contract is able to do execution conditionally on that. It's sort of like almost like an oracle, but people have called that the ZK coprocessor. But all of these things boil down to the fact that in blockchains, you're very resource restricted. So the resource restrictions give you a lot of incentive to have these kind of separations between, like, someone does high power compute, but someone can verify it without much compute power themselves. But most people are really just doing interactive proofs and like not the ZK part. The ZK part is the private part. The interactive proof part is proving to you I have a solution to some problem. And so the reason people are excited about it is like blockchains are really the first thing where ZK actually is like, it's very clear why you need it. It's almost like very direct. And for a lot of these other applications, like people want things like ZK or FHE or MPC and like private machine learning, the scale at which we can do ZK is just not that high. And we are not like, there's some heroic efforts and people have been able to get some language models actually snarked very recently. But I think the blockchain use case is like, it'll go live now, whereas the machine learning use cases are probably like 3 to 5 years ahead in the future, like in production. So just, yeah, I don't know if that answers all the parts of your question. But.
Yeah, no, that very much does. One, I guess, follow-up question to that would be, where do you see this moving on chain? Not on the language model side, not on the not on the outside of blockchain side, but within crypto. How do you see these being applied? Because I know there's a lot of big teams working on this now with a ton of funding. They're optimizing hardware, they're doing all these different things. How do you think people are going to try and have them be applied at a practical, maybe like consumer level?
Yeah, I mean, I think certainly the number one thing is like mobile wallet experience should get better, which is kind of a boring use case. Like there actually already exists a ZK wallet, but for a network that no one really uses in the Plumo wallet in Stella. Yeah. But I really do think like wallet experiences get better. The other thing is I think cross-chain composability gets somewhat better in the sense that instead of having to have one virtual machine have to be able to emulate another virtual machine completely, all you need, everyone just like agrees on a particular proof system, and you have each side has their own code for verifying it. But as long as that's implemented correctly, you know that you can verify any statement either can prove without having to know every detail of every piece of code. So that part is useful. But I think, and I gave a talk about this kind of recently. I think like the problem with ZK stuff is like you can't really explain to like a non-technical, non-crypto person like why you would care about it. And I think
Until
that's
they
sort of
do, until the world if the world gets into a state where they very much do. But I agree, in our current sort of world, that's not the case.
yeah, but like actually one particular set of examples, and I think there's some recent research on this. One is papers that I've written recently, and papers that some other people have written recently, like Fiat, actually, from Fiat Transform, is that there's a whole class of mechanisms where by using ZK to execute the mechanisms, you can provide explicit price guarantees or like auditability manipulation guarantees.
Mm-hmm.
And those types of guarantees are economic guarantees. And you can show that without the ZK part, you have strictly worse pricing. And so what that means is like for auctions, particular types of auctions where you want, so there's, without diving too far into the auction thing, the idea is that you kind of might want two properties out of an auction. You want, or three properties. You want sellers, the seller of the item in the auction, to not be able to add fake bids and push the price up without them winning it, or censoring communication between bidders and causing the price to go. You might want buyers to have some properties where they actually have to bid what they think the value is, what their value is. And you may want to have another concern, which is bounded communication complexity. You don't have to keep communicating back and forth. So one really important thing about ZK that's actually worth noting is that the non-interactive part of snarks of these proofs means that you had this thing that had many rounds of communication, and I turned it into one round of communication. That's extremely important for blockchains because blockchains have extremely expensive communication complexity. If I have to keep doing many rounds, things don't work. Arguably that's one of the reasons Uniswap was so successful versus other forms of on-chain trading, because it has low communication complexity. But the idea is that ZK compresses this communication complexity, and so those three properties you want in an auction, it turns like economists sort of showed you can't get all three, assuming unbounded adversaries. But we showed, assuming some types of ZK commitments, you can get all three of those properties, and you can also get bounds on the you can basically show that sellers can't manipulate the revenue. Now, you might say, okay, this is all theoretical, but the DOJ is actually suing Google right now over the fact that over the last 10 years, they were effectively adding fake bids in their auction and causing the prices to go up for exactly this type of thing. You can't really tell when the seller is doing it. You have to like, over 10 years, all the market participants have to like talk to each other to figure out like, hey, I didn't bid that much. Wait, I didn't bid that much either. How did it get sold for higher? And these types of guarantees, these economic guarantees, I think that come from the ZK pieces of a mechanism are very tangible, right? It's like, I can just show you the price improvement, and consumers like price improvement.
Oh, that's fascinating. I've only ever thought of it from the perspective of privacy and compute constraint. So this is really cool. Yeah, definitely send the paper, and I'll put it in the description as well.
Yeah,
just to have it.
Someone bought a URL for it, so
nice, perfect. All right, let me just save that so I have it. Cool. I only have one more question for you on this one, Tarun, although I would love to do another episode more around company building and founding something and perhaps that side of the world as well. But my
Sure.
my last question for you for now is, if you, or not advice, are there any sort of habits or lessons or things that you've found have improved your life significantly over the last 5, 10 years? This could be in the world of crypto, of business, of founding a company, of health, of wealth, whatever comes to mind when I ask you this question.
Yeah. Um, Something I think that I have strongly believed over my professional life, but I think that has guided me a lot, that I think people forget about often, especially in startup land, is you only have one reputation, and you should try to do things that never really damage it. And I think a lot of people don't do that, right? They're willing to like trade reputation for short-term gain at different points, and that, I would say, that inevitably does bite them. And to me, that's sort of one thing that I really try as hard as possible to do and live by, because once you start with that as your axiom, then you can induct a bunch of other things that you shouldn't do or should do. Maybe it's a lame answer, but
No, I think that's a really good insight, especially in our industry, because you're so right. Everyone is so short term with their thinking. It's honestly such a shame, because I don't know about you. I'm here for the long run. I want to be here, hopefully this all survives, right? But I want to be here decades from now, still working on this stuff, still interacting with the same amazing people and new people that have come into the space. So I completely agree. I think that's a very good insight. And thank you so much for coming on. I guess final question: is the air quality better, or are you still dying over there?
nah, it's good. It's
Okay,
good
okay.
now.
The blue
I
pack.
only wore a mask for like 1.5 days, but it was definitely just like very surreal.
Blade Runner type.
Yeah, it was very surreal. It was very surreal, but no, now it's come down. It rained a bunch too, so that like helped. So
Okay.
yeah,
It's really good to hear. Yeah, I was sad for all my New York friends suffering through that.
yeah, yeah.
Cool.
It was worth it though to see. It's like my the other favorite kind of end of the world thing in New York I really loved was like during the pandemic, summer 2020, just like biking through Times Square at like 10 p.m. and there's all the lights are on and there's no one there except two kids like who are really high. Uh and like the cops weren't even in the like police station in time. Like that was like, whoa, did I just like drive through a bike through an apocalypse? But yeah,
I don't know
those
why.
those are
Have you read? Sorry to interrupt. Have you read Master and Margarita by
no,
Bulgakov?
what's that?
Oh my god, one of my favorite books of all time. You should highly, highly, highly recommend it. It's probably the best critique of the Soviet Union that I've ever read, while being an incredibly entertaining fictional story, where the devil visits Moscow. And there's a scene which is a little bit of this representation of being alone in an enormous city at night, and it made me think of that. But I highly recommend that book to you, to any of the listeners.
Yeah, that's amazing. I just am looking at the
Yeah, phenomenal book, like truly.
I didn't know it's like a banned book also
Oh yeah,
in
yeah,
some
yeah.
places.
It took from when he wrote it to when it was allowed to be published, especially in Russia. I don't remember. There's a lot of years that passed. That's for sure.
Yeah,
Um,
so interesting.
cool. All right. Well,
Cool.
thank you so much for coming on. Take
Thanks
care,
a
Tarun.
lot.
Have a good one.